Next topic is proof of division algorithm. So what is the division algorithm? We know this. This is the division algorithm theorem that if a and b are any two integers, and if suppose a is not equal to 0, then there exist a unique integers q and r, so that b is equal to aq plus r. That is, if we divide the larger number, suppose b is larger number, then by smaller number, a and b are the any two numbers, and a is not equal to 0. Divisor is not equal to 0. If we divide this b by a, then we have some quotient and we have some remainder, and remainder is always less than the divisor, and is greater than or equal to 0. So this theorem and the proof of the theorem both are important uh, as far as the exam concerned. In the point of view of examination, your exam term and examination, university examination, this theorem is important. That is, the question on the theorem is what? State and prove division algorithm theorem. So this is the statement of the division algorithm, and it is very simple. And by using this, we already solved the greatest divisors example. That is, suppose we are given the two numbers. Suppose we are given 51 and suppose 8. That is, if we divide this 51 by 8, then what is the quotient? 6 is the quotient and 3 is the remainder. Okay, the remainder is always less than divisor. If we have 8 remainder, we have suppose here instead in the place of 3, if we have suppose 8, then it is remainder? No, because 8 divides to 8, and the quotient suppose here is 1, and then 8 by 8, right? 8 minus 8, that is 0. 0 is the remainder. Suppose here we have number 9, then it is not remainder, because if we divide number 9 by the 8, okay, that is the 1 is the quotient, and then write 8 below the 9, and then 9 minus 8 becomes 1. 1 is the remainder. So remainder, when we say this number is remainder after division, when we say this is the remainder, if it is strictly less than divisor, if it is 8 or larger than 8, it is not remainder. That is, the remainder is always strictly less than the divisor. If the divisor is negative, then write here mod. Write here mod. That is the minus 8. That is the mod of minus 8 is plus 8. Okay. So this is the theorem that if we are given two numbers, suppose 51 and 8, then we have some quotient and we have some remainder. And so in this theorem, this 6 is denoted by q, and this remainder 3 is denoted by r. That is, this r is what? And the remainder is not negative. Okay, if we divide, suppose this we can continue the question. If we divide 8 by 3, suppose here we write 1 and here write 8, then 3 minus 8, that is minus 5, is remainder? No, because remainder is always greater than or equal to 0. Remainder after division of any two numbers, the remainder is what? Is either 0 or greater than 0. Okay, and strictly less than the divisor. So this is very simple theorem. That is, if we are given two numbers, and then if we divide the larger number by smaller number, then we have some quotient, we have some remainder. Okay, so this is the division algorithm. Already by using this, we solved the greatest common divisors examples. Okay, so by using repeated use of division algorithm, we find the greatest common divisor of two numbers. Okay. And what is well ordering principle? That is, if S is a non-empty subset of non-negative integers, that is the set of natural numbers union 0. That is set of natural numbers including 0. That is set of whole numbers. Suppose S is any non-empty subset of that set, whole numbers or set of natural numbers, then that set has at least element. That is, there exists some number a belongs to S such that a is less than or equal to b. That is, a is the smallest number in that set. That is, a is less than or equal to b for all b belongs to S. That is, that number is the smallest number in that set. Okay, but when it happens, if the set is subset of natural numbers or set of non-negative integers. So what is the difference between non-negative integers and natural numbers? The set of natural numbers contains 1, 2, 3, 4, 5, 6, 7 up to infinity, and the set of non-negative integers contains 0, 1, 2, 3 up to infinity. That is one more element. If you add a 0 in the set of natural numbers, then we say it is a set of non-negative integers. Okay, and if this is the subset of what set of non-negative integers, the subset of non-negative integers. And what is the least element? 0 is the least element, because 0 is what, less than or equal to all the elements of this set. But these two 6 is not subset, actually subset of this set of natural numbers or set of whole numbers. And we cannot say we does not have the minimum element in this set. Okay, so when we say when the least element exists in the set, if the set is subset of natural numbers or subset of non-negative integers. This is the well ordering principle, and this is the division. Now we have to give the proof of, and already this definition that when a divides to b, when we say a divides to b, if b expressed in the form a into some integer, that is the remainder is 0. That is, if you divide b by a and if you have remainder is 0, then we say a divides to b. For example, 2 divides to 8. Why? Because 8 expressed in the form 2 into 4, some integer. K must be integer. 2 divides to 9, no, because 9 does not divide by 2, because you cannot write 9 in the form 2 into some integer. This 4.5 number 4.5 exists at this place, because 2 into 4.5 is 9, but this 4.5 is not integer. We can write 9 in the form of division algorithm, that 2 into 4 plus 1. How we can write 9 2, if we divide 9 by 2, then we can write 9 as 2 into 4 plus 1. That is 9. Okay, and that is the division algorithm theorem. That is 1 is the remainder. But if 1 is the remainder, if the remainder is 0, then we say divides. Okay, so these are some examples. And if when 5 divides to, what are the divisible by 5 numbers? What numbers are divisible by 5? We know that 5 and larger than number 5 are divisibles of 5. Okay, that is 5. What are the numbers divisible by 5? Are 5, 10, 15. These are the numbers divisible by 5. But 5 does not divide less number. 5 does not divide 4. 5 does not divide to 3. 5 does not divide to 2. 5 does not divide to 1. But 5 divides to 0. Only one number which is less than 5 and which is 0, such that 5. Why 5 divides to 0? Because by using this definition, the 0 expressed in the form 5 into, why 5 divides to 0? Because the 0 expressed in the form 5 into some integer. What is that integer? 0. And therefore 5 divides to, when the number divides to smaller number, that is if a divides to b. Suppose we have a divides to b, we are given a divides to b, and this b is strictly less than a. B is strictly less than a, like this, then b must be 0. Then b must be 0, because if the larger number divides to smaller number, then the smaller number must be 0. So remember these concepts, divisibility and these concepts, these are useful in the proof of this division algorithm theorem. So what is the division algorithm theorem? If a and b are unique to integers and a is not equal to 0, then there exists unique integers. This word is important again. Unique integers q and r, such that b is equal to aq plus r. That is, if we are given suppose 51 and 8, then the answer question q is what, 6 and remainder 3. So the answer of all the students, that is this q and r are same. That is, this q and r are unique. That is one and only one. Answer of all are same. That is, if we are given two numbers, suppose b and a and b, and if we divide b by a, then the question and this remainder, that is q and r denoted here, q and r are unique numbers, unique integers. Okay, and where r is obviously less than, strictly less than divisor and greater than or equal to 0. Remainder is always less than divisor. That is, if 8 is divisor, then remainder is what? Here is 8 is divisor, then remainder must be 7, less than, strictly less than 8. That is, it is 7, 6, 3, 4, 0. It is not negative. Okay, so the proof of division algorithm. The proof is in the two cases. So suppose a is not equal to 0, means a is what? A is either greater than 0 or less than 0. So assume that in first case a is greater than 0, and in second case we assume a is less than 0. Then define the set S is equal to b minus x belongs to z such that b minus x is greater than or equal to 0 and x is the integer. So this is the definition. So remember this definition, b minus x belongs to z such that b minus x, this is constructive part. So remember this definition of yes, b minus x belongs to z, that is integer, and b minus x is greater than or equal to 0 and x belongs to z. Now we have to show this yes is non-empty subset of this set n union singleton 0, means set of natural numbers contains 1 2 3 4 5 union 0, means that this is set n union singleton 0 means the set of integers, non-negative integer, that is 0 1 2 3 4 5 up to infinity. Now we have to show this yes is non-empty subset of this. Obviously this is subset of n union singleton 0, this yes, because yes contains integers and all the integers b minus x members of this set are greater than or equal to 0, means this yes is what? Yes is subset of b, obviously subset of n union singleton 0. Now we have to just show that this yes is non-empty. That is when set is non-empty if the set contains at least one element. Now we find one element in this set, so construct that one element. So b is greater than 0, a is greater than 0 here. Our assumption is a is greater than 0, implies a is greater than or equal to 1 because a is integer. And what are the integers greater than 0 are 1 2 3 4 5. So a is strictly greater than 0 means a is, what is the value of a? Is either 1 2 3, it is not 1.2 or 1.3. Greater than 0 means because a is integer. And so what are the numbers greater than what are the integers greater than 0? Either 1 2 3 4 5, these are the what integers greater than 0. So a is greater than 0 implies a is greater than or equal to 1. Then multiply both sides of this inequality by mod b. So mod b into a is greater than or equal to mod b into 1, and then add b in both sides. So b plus mod b into a is greater than or equal to b plus mod b, and b plus mod b is always greater than or equal to 0 because any number plus its magnitude, its mod number plus, suppose b is 5, then what is 5 plus mod 5? 5 plus mod 5 is what? Is 10, that is greater than 0 number. Suppose b is minus 5, negative number, because b is any integer, it may be negative. So if b is suppose minus 5, then what is the mod of minus 5 is plus 5, and then minus 5 plus 5 becomes 0. So b plus mod b is what? Always greater than or equal to 0. It is not negative number, it is always either 0 or greater than 0, and therefore b here adjustment, write this b minus in bracket minus b into a, and is greater than or equal to 0, right here 0, here greater than or equal to 0 because it is greater than or equal to 0. And this number is of this form b minus ax. So what is b minus a, and this is x, suppose this minus b is x, then this number is of the form this b minus a into minus mod b is of this form b minus ax, b minus a, and this is x. And so this is the element of yes because it is greater than or equal to 0. This condition is satisfied by this element b minus mod b into a is greater than or equal to 0, and this minus mod b is integer. This x, value of x is what? Minus mod b, and mod b is integer, therefore mod b is integer, and therefore minus mod b is also integer, and therefore this is the element of yes because this b minus mod b into a satisfies all these property of this set. So when element becomes an element of set yes, if it is of the form b minus x, and this b minus ax is greater than or equal to 0 and x is integer, so this satisfies all the conditions, that is b minus mod b into a, this is greater than or equal to 0 means this condition, and this is of the form b minus ax, and x, this x is what? Is integer, and therefore this is the element of yes, and therefore yes is non-empty. Okay, why yes is non-empty? Because yes has at least one element, and therefore yes is non-empty, and it is subset of n union singleton 0 because its definition indicates that it is subset of n union singleton 0. And therefore, by well ordering principle, what is the well ordering principle? Every non-empty subset of n union singleton 0, that is set of non-negative integers, every subset of set of non-negative integers has least element, and therefore S is non-empty subset of n union singleton 0, and therefore by well ordering principle S has least element. And let it be R. Suppose R is the element of S and it is the least element of S. That is what has least element, say R. That is the least element of S exists because of well ordering principle, and suppose that element is R. Then what happen? R is the element of S because R is least element of S, and R is less than or equal to Y. R is less than or equal to Y for all Y belongs to S. That is, this is the property of least element. R is least element in S means R is what? Is smallest element of S. It is less than or equal to all the remaining elements of S. All the elements of S. That is what? R is least element means R is what? Less than or equal to Y for all Y belongs to S means what? R is the smallest element or least element of S. It is less than, it is smaller than all the remaining elements. Okay? But R belongs to S. And so it implies it is of this form b minus x, so for some x, and so R is what? R is the element of S, so it can be written in the form b minus a into some integer x, y, z, take any notations here. So R is the element of S, therefore R is written in the form b minus aq for some q belongs to Z. Instead of x here, q is later used. And so b is equal to, shift this minus aq in right side, so b is equal to, what do we have? B is equal to aq plus R. Now obviously R is what? R is the element of S means R is greater than or equal to 0, because the property of S is what? This set contains elements greater than or equal to 0, means R is greater than or equal to 0. So the proof of this up to this complete. B is expressed as aq plus R, where R is what? Greater than or equal to 0. So what is the remains to prove? Now it remains to prove that R is strictly less than mod A. A is greater than 0, and therefore mod A and A both are same. Mod A and, because A is greater than 0. Suppose A is 5, then mod 5 and 5 both are same. If the number is greater than 0, then its mod is itself, because mod of 5 is 5, mod of 3 is 3, mod of 4 is 4. Okay. And so now we have to prove actually this b is equal to aq plus R, where R is strictly less than n greater than equal to 0. And here what we have? B is equal to aq plus R and R is greater than 0. So it remains to show that R is strictly less than mod A or A. So next sentence. Now it remains to show that R is strictly less than A, because mod A, actually we have to show R is strictly less than mod A, but A is greater than 0, therefore mod A and A are both are same. And the proof of this is by contradiction method. What is the contradiction method? We have to show R is strictly less than A. We assume its negation. So what is the negation of R less than A? R is greater than or equal to A. So now suppose or assume that R is greater than or equal to A. We have to show actually R is less than A, but the proof is by contradiction method. That is, we have to show R is less than A. Now to show R is less than A, strictly less than A, assume its negation. So what is its negation? R is greater than or equal to A. R is not less than A. What is the negation of R strictly less than A? R is not strictly less than A, means suppose R is greater than or equal to 0. And then what happens? If we have some contradiction. In this method, we have some contradiction, because, and then we say that our assumption is wrong. So what is our assumption? It's negation. R is less than A. Its negation is what? R is not less than A. Means R is greater than or equal to A. And then R minus A. So A is larger number. R is larger number than A. And so if we subtract smaller number from larger number, then answer is greater than or equal to 0. Or shift or subtract A from both sides. So R minus A is greater than A minus A means 0. But R minus A, what is the value of R minus A? R is what? R is from this, R is B minus AQ. So substitute B minus AQ minus A is equal to write B minus AQ minus AQ and minus A, take A as common, so minus in bracket Q plus 1A, and then this is the suppose Q plus 1 is suppose X, then B minus AX, this number is of the form, what is the value of R minus A? B minus AX type, and this R minus A is greater than or equal to 0, and therefore this R minus A satisfies all the properties of this set S. So when any element is the element of S, if it is of the form B minus X, so this element R minus A is what is of the form B minus AX, and this R minus A is greater than or equal to 0, that is this property, the number is greater than or equal to 0, and therefore this is the form of element of S, and therefore R minus A belongs to S. This R minus A is the element of the form of element in S, and therefore R minus A belongs to S, because this R minus A satisfies this property, that is it is of the form B minus X, and this B minus X is greater than or equal to 0. So R minus A becomes the element of S. But what is your assumption? This is a contradiction to our assumption, because R is the least element of S, and since A is greater than 0, R minus A is strictly less than R, because A is not 0 when these two are same, if A is equal to 0, but A is not equal to 0, A is greater than 0, or proof is what? First A is greater than 0, case 1 is A is greater than 0. So R minus A is strictly less than R, and which is contradiction to the choice of R, because what is R? R is the least element of the set S. That is, no element less than R exists in the set S. But here we have R minus A is strictly less than R, and R minus A is the element of S, which is not possible, because R is the least element of S. No number less than R exists in S. But here we have the number less than R and exists in S, and this is not true. This is contradiction and to the choice of R. And why this contradiction arises? Because our assumption is wrong, that R is greater than or equal to 0. And so then what is the correct? That R is not greater than or equal to A, means R is less than A. So this procedure is called a contradiction method. That is, the proof is by using contradiction method. So what we have? R is less than. This is wrong. R is greater than or equal to A is wrong, means what is correct? R is less than A. And therefore, we join this statement. Therefore, we have B is equal to AQ plus R, where R is greater than or equal to 0 and strictly less than mod A or A. In this case, A is greater than 0. Therefore, mod A and A both are same. Okay. Then case second, we assume this A is what? Less than 0. But if A is less than 0, then mod A is greater than 0. Because mod of negative number, suppose A is minus 5, then its mod is what? Plus 5. And replace A by mod A in the case number 1. So what do we have? B is equal to, replace A by mod A, mod B. We have some question and we have some remainder. So we did not question by Q dash and remainder by R, where R is what? Less than A, mod A, and greater than or equal to 0. And what is mod A then? Mod A is minus A, because suppose A is less than 0, means suppose A is minus 5. Then what is the mod of minus 5? It is minus 5. A is less than 0. Then what is the mod? If A is greater than 0, then its mod is itself. But if A is less than 0, if number is negative, suppose here A is minus 5. Then what is its mod? Minus, in bracket write minus 5. Then we have the answer plus 5. We know that mod of minus 5 is plus 5. Mod of minus 5 is plus 5. How it's come? Mod of minus 5 is what? Minus 5. Therefore, so if the number is negative, then its mod is what? Mod of A is minus A. And if A is positive, then mod of A is itself A. So replace here mod of A by minus A, and absorb this minus sign in this Q dash, and write this minus Q dash as Q. And therefore what we have? B is equal to AQ plus R. R is strictly less than mod A and greater than 0. That is, if A is negative, then also we have this B is equal to AQ plus R. and in both cases we have the integers q and r such that b is equal to eq plus r is strictly less than mod a and greater than or equal to 0. And this proof that if we are given two integers q and r, then there is a and b, then there exist integers q and r such that b is equal to aq plus r. Okay, now we have to prove the uniqueness of this q and r. Suppose this q and r exist double, that is we assume that b is equal to aq plus r and b is equal to aq dash plus r dash, that is these q and these r are not unique. Suppose we assume that there exist two quotients and there exist two remainders, and now we have to show q is equal to q dash and r is equal to r dash to show the uniqueness of q and r. That is we assume q and r not unique. Suppose we assume that q there exist two q's and two r's. Suppose they're denoted by qr and q dash r dash, that is b is equal to aq. Then we have to show q is equal to q dash and r is equal to r dash. This is the uniqueness part of q and r. We assume these q and r not unique. They exist two pairs of these integers. Then subtracting these two equations, b minus b is 0, a take a as common, q minus q dash plus r minus r dash. Okay, and where obviously r and r dash are what, greater than or equal to 0 and less than mod a. Okay, then what is the value of r minus r dash? Substitute this to RHS minus a q minus q dash, or absorb the negative sign, right? Q minus q dash as q dash minus q, and then this r minus and r dash expressed in the form a into some integer q minus q dash. Q is integer, q dash is integer, and therefore q dash minus q is also integer, and therefore r minus r dash expressed as a into some integer means a divides to r minus r dash by using this definition. So when we say a divides to b, if b expressed in the form a into some integer, and if b expressed in the form a into some integer, then we say a divides to b. A divide. If you write b as a into some integer means a divides to b, like that. So here is the what do we have? R minus r dash is equal to a into some integer means a divides to r minus r dash. But this r minus r dash is what? R and r dash both are less than a, and therefore r minus r dash is also less than, strictly less than a. That is divisor here is a, and this divides to smaller number. What do we have? Larger number divides to smaller. This number is less than a. This is small than a. So when larger number divides to smaller number, then smaller number must be 0. Here is the when 5 divides to what number smaller than 5, only 0 is the number that 5 divides to 0, smaller number. That is if a divides to b, and if b is less than a, that is if a is greater than b, if the divisor is greater than this number, then this b must be 0. So when in the only one case, larger number divides to smaller number if the smaller number is 0. So here we have that a divides to r minus r dash, and r minus r dash is strictly less than a means r minus r dash is 0. That is we have r is equal to r dash, and if we substitute here r is equal to r dash here, then what do we have? R minus r dash means r equal to r dash, or r minus r dash is 0. Then we have 0 is equal to a q minus q dash. A is not equal to 0, so if we shift a, then we have q minus q dash is 0, and therefore q dash is equal to q, because a is not equal to 0. So substitute r minus r dash here 0. First we have a into q dash minus q is equal to 0, and a is not equal to 0 means q dash minus q is 0, because if the multiplication of x into y is 0, then either x is 0 or y is 0. One of them is 0. A is not equal to 0 means q dash minus q is 0, and therefore q dash is equal to q, and hence these q and q dash q and r are unique. If we take two q and q dash, then q and q dash are same, r and r dash same. That is, disprove the uniqueness, and then this completes the proof of the theorem. So this is the proof of the theorem. In the next lecture we will see the proof of theorem on the greatest common divisor.